This is hypothesis testing for proportions. So these are proportion problems. We'll have some categorical variable, just like always. We'll have some population, what we're calling success. And we defined little p to be the population proportion of success. Our setup is we think we know what p is. We believe, for some reason, previous testing, whatever, we believe the success rate is some number. We call this P naught, and that's what we believe is the success rate. Then we go out and we do a new sample, and the sample contradicts that number. It says the success rate is some different number, maybe less than that, maybe more than that, maybe just not that number. So in our sample, just like always, X is the number of successes in the sample, N is the sample size, and P hat is the success rate in the sample. So we thought the population success rate was some number, P naught. The sample says, no, it's actually less than that. Maybe the sample has a lower success rate than we believed, or more than. Or sometimes we don't care if the rate went up or down. We just care if it's different. We're just looking for a difference. We call these two-sided hypothesis tests. So we have two possibilities, two hypotheses. Our null hypothesis, we call that H naught, or the null, is what we used to believe. The success rate is that number that we used to believe. We used to believe that 30% of M&Ms are green, so P equals 0.30. We did our sample, and the sample says, oh, that's not true anymore, so we have an alternative hypothesis. Maybe we now think possibly the success rate is lower than we used to believe, maybe greater than, or sometimes we don't care if the rate went up or down. We just say, oh, it changed. And the sample tells us which one of these three, the sample and the wording of the problem, tell us which one of these three alternative hypotheses to pick. Our goal in hypothesis testing is to try as hard as we can to prove the null hypothesis false. If we do that, if we prove the null false, there's only one possibility: the alternative must be true. If we can't prove the null false, then we failed at our job. We draw no conclusions. We never, ever, under any circumstances, accept the null hypothesis. Hypothesis testing is a lot like a criminal trial. When someone goes on trial, the prosecutor's job is to try as hard as they can to prove that person guilty. And when the prosecutor fails, the defendant is found not guilty. Nobody's ever found innocent. You never leave court going, oh, I proved my innocence. No, the prosecutor is trying to prove the person guilty. If the prosecutor fails, the person's found not guilty. It's the same here. We're trying to prove the null hypothesis false. If we succeed in that, then we won. We get to accept the alternative. If we fail to do that, then we draw no conclusions at all. Okay, here's the math that happens in the background. We're going to do everything on the calculator, but the math is we assume for the moment that the null hypothesis is true, that P actually equals P naught. Then we would find the probability of getting that sample that we went and took. Same as always, we draw a picture, find a z-score, normal CDF. If that sample has a very low probability of happening, well then either it was a very weird sample or the null hypothesis must have been false. Our original assumption must be false. If that sample does not have a low probability, if it's a sample that happens all the time, well then we haven't gotten any new information and we'll draw no conclusions. So we'll do all this on the calculator, and the calculator will spit out our p-value. The p-value is the probability of getting that sample, assuming the null hypothesis is true. Low p-value is strong evidence that the null must be false. If the p-value is low enough, we reject the null and accept the alternative. If the p-value is not low enough, we fail to reject the null. We draw no conclusions. Those are the only possibilities. Low p-value, reject the null. High p-value, fail to reject the null. Never, ever, ever accept the null hypothesis. Well, now, what do we mean by low enough? I keep saying low enough here. That's a number we decide ahead of time. Before we start, we decide how low we think is low enough. If our p-value is under that, we reject. If it's not, we fail to reject. That's called the alpha level. Typical alpha levels are 10%, 5%, or 1%. We will usually use 5. That's kind of the most common. If the p-value is below your alpha, reject the null, accept the alternative. If the p-value is greater than alpha, fail to reject the null. Never, ever, ever accept the null hypothesis. So p-values are kind of counterintuitive. The lower the p-value, the stronger the evidence against the null. Low p-value is strong evidence. The p-value is not the probability for or against the null. It has nothing to do with the probability of the null. It's the probability of getting that sample we got if the null were true. If it's a very low probability, then either it's a weird sample or the null must be false. Always keep in mind too, the hypotheses are complete mathematical sentences. They're not numbers. For example, we might say our null hypothesis is that p equals 30%. That's a complete sentence. This says we believe that 30% of M&Ms are green. We would never write something like this. We would never say, I believe equals 30%. What equals 30%? That doesn't make any sense. The null hypothesis is always p equals a number, and then the alternative will be p is different from that number. Maybe less than that number, maybe greater, maybe not equal to. Same number though. The null hypothesis is what we believed before we did the sample. And then once we look at the sample, that tells us which alternative to use.